On the morning of September 1, 1859, a 33-year-old English astronomer named Richard Carrington was doing what he did every clear day, projecting an image of the sun onto a screen and drawing the dark spots on its surface. At 11:18, in the middle of a huge sunspot group, two beads of white light flared up, so brilliant that he thought sunlight had leaked through a hole in his equipment. It hadn't. He was watching, with his own eyes, the most powerful solar flare ever recorded. 17 hours later, the sky over the entire planet caught fire. This is the story of the Carrington Event, the day the sun touched the Earth, and why scientists quietly consider its return one of the most underestimated threats to modern civilization. What Carrington saw was the flash of a magnetic explosion on the sun, releasing the energy of billions of atomic bombs. And behind the flash came the real projectile, a coronal mass ejection, a billion tons of magnetized plasma fired out of the sun like a cannonball the size of a planet. These clouds normally take 3 or 4 days to cross the distance to Earth, if they hit us at all. The 1859 cloud arrived in 17.5 hours. It was one of the fastest ever recorded because a smaller eruption days earlier had swept the road clear in front of it. When it hit, the Earth's magnetic field rang like a struck bell. The aurora, normally imprisoned near the poles, spilled across the entire sky of the planet. It was seen in Cuba, in Panama, in Colombia, virtually on the equator. In the Rocky Mountains, gold miners woke at 1 in the morning and started making breakfast, convinced the glowing sky was dawn. In cities along the American coast, people read newspapers at midnight by the light of the aurora. Witnesses described the sky as blood red, as if the atmosphere itself were burning. And then the world's newest technology began to behave as if possessed. The telegraph, barely 15 years old, was the only electrical network humanity had. The storm's shifting magnetic field induced rogue currents in thousands of kilometers of wire. Operators were thrown back by sparks from their equipment. Telegraph paper caught fire on the desks. Machines kept transmitting after being disconnected from their batteries, running on the storm itself. 2 operators in Boston and Portland held a 2-hour conversation powered entirely by the aurora. The planet's magnetic field had become the network's battery. In 1859, that was the entire damage report, some scorched telegraph desks, and a light show for the ages. Because in 1859, electricity was a curiosity. The question that keeps space weather scientists up at night is simple. What happens when the same storm hits a civilization that runs on electrons? We got a preview in March 1989, when a storm a fraction of Carrington's size collapsed the power grid of Quebec in 90 seconds, leaving 6 million people in the dark. A larger hint came in 2012 when a Carrington-class cloud erupted from the sun and crossed Earth's orbit through the exact point where our planet had been 9 days earlier. NASA's assessment was blunt. If the eruption had happened 1 week later, we would still be picking up the pieces. Run the Carrington scenario against today's world, and the cascade is sobering. Geomagnetic currents flow into power grids through their grounding lines, saturating the massive high-voltage transformers that form the backbone of every network. These transformers are the size of houses, custom-built, and replacements take months to years. Studies for the American insurance market have estimated tens of millions of people without power for weeks or longer, and total costs in the trillions of dollars. Satellites would be dragged and damaged in a swollen atmosphere. GPS and everything silently synchronized by it, from shipping to financial markets, would degrade. The internet's ocean-spanning cables are vulnerable too, not in the fibers themselves, but in the repeaters that power the signal across the seabed. And here is the detail that gives this story its edge. This is not a question of if. The sun produces Carrington-class eruptions with some regularity. Space is simply very big, and Earth is a small target. Ice cores and tree rings suggest even larger events, like the extreme cosmic ray spike of the year 774, have struck the Earth before. One respected study put the odds of a Carrington-class hit in the next decade at roughly 1 in 8. You would not board a plane with those odds. The good news is that we are no longer blind. A fleet of spacecraft now watches the sun continuously, and satellites stationed upstream of Earth can give us 15 to 60 minutes of warning of a cloud's final magnetic orientation, the factor that decides whether it slides past or strikes deep. Grid operators can, in principle, protect transformers by shutting sections down before the wave hits. The 1859 storm gave humanity a harmless preview, a century and a half early, on the only piece of technology we had built so far. It was, in a sense, the gentlest possible warning shot. Richard Carrington died in 1875, never knowing what his 2 beads of white light would come to mean. Today his name is attached to the benchmark disaster of the space age, the storm every forecaster measures against. The sun that morning showed us exactly what it can do. The only question it left open is whether we will be ready the next time it does. The last time the sky burned, we read newspapers by its light. Next time, the lights will be ours to keep on. If this story earned your time, subscribe. The archives are full of warnings we almost missed.